Now that you know what an HSM is, we'll zoom inside it. In this module, we'll treat the HSM like a transparent vault and look at how it's organized. Partitions, roles, policies, and the paths applications use to access keys, without ever seeing those keys directly. When we talk about an HSM, it's easy to picture only the metal box in the rack. That hardware is essential for tamper resistance and strong randomness. But it's just the foundation. In real projects, most of your security design lives in the logical vault. How you define partitions, users, and roles, security policies, and cryptographic domains inside that physical device. Logically, there are three big ideas to keep in mind. First, isolation. Every key and every operation lives in its own cryptographic room, so one tenant or app can't touch another's material, even accidentally. Second, control. Who can log in, which roles they have, and exactly what each role is allowed to do. Third, connectivity. The secure API path between your applications and those protected keys. Designs that get these three pillars right are much easier to scale, operate, and certify. A core strength of HSMs is that one physical device can safely host many independent tenants. Partitions, or cryptographic domains, are how this is achieved. Each partition has its own keys, crypto objects, configuration, and policies. An application or team granted access to one partition cannot see or use material in another. Even backup and restore are usually scoped per partition. The main takeaway: partitions provide strong isolation for keys and all other sensitive state. Multi-tenancy means taking one physical HSM and carving it into multiple isolated vaults. Each vault or partition belongs to a specific business context: payments, PKI, a dev environment, or another clearly defined domain. The non-negotiable rule is that tenants must never see or influence each other's keys. If a payment key can even accidentally touch test systems, your assurance is gone. So when you design partitions, mirror your real business boundaries and risk levels, not just convenience or cost-saving consolidation. An HSM is not governed by a single superadmin account. It uses a hierarchy of roles. The security officer owns the box itself, initializing it and defining global settings, but never handling application keys. The partition administrator controls just a partition, creating it, managing its keys and policies, but not actually using those keys for crypto operations. Crypto users are typically applications. They can sign, decrypt, or unwrap keys, but can't change the security setup. This separation of duties enforces least privilege and prevents any one person from unilaterally controlling critical keys. Access to an HSM partition is never just log in and go. Think of it as passing through several gates. First, applications authenticate with basic credentials such as passwords or API keys. Administrative actions step up to stronger factors like smart cards or hardware tokens. For the most sensitive operations, such as loading master keys, you add an M of N quorum, where multiple people must present their credentials so no single admin can act alone. This layered authentication is what prevents silent, unauthorized changes to your HSM. HSMs don't just store keys. They enforce rules about how those keys can be used. There are two important layers of control. At the global level, policies might require FIPS mode, dual control for critical actions, or ban certain algorithms entirely. At the key level, attributes like non-extractable or sign-only make it impossible to export a key or decrypt with it, even if you're an admin. Many of these settings are one-way, so you can tighten security over time, but you can't silently weaken it later. A typical HSM journey follows 4 steps. First, install the device under strict procedures. Rack it, cable it, and ensure only authorized staff are involved. Next, initialize it by creating security officer credentials, loading initial secrets, and, if required, enabling FIPS mode. Then, carve it into partitions, assign administrators to each, and apply baseline security policies. Finally, integrate it with applications by installing client software, configuring APIs, setting up logging, and testing that keys never leave the hardware boundary. Between your applications and the HSM, there's always a client layer acting as a smart middleman. Your code calls a standard API. Sign this, decrypt that, generate a key. The client software figures out which HSM to talk to, balances traffic across multiple appliances, and maintains encrypted channels over the network or PCIe. That indirection is what makes HSMs scalable and maintainable. You can add or replace hardware, or fail over between devices without changing application logic at all. PKCS number 11 and KMIP solve related but different problems. PKCS number 11 is a low-level C-style API used directly by applications. You load a local library, send raw crypto operations, and you're very close to the HSM. That gives you fine control and performance, but also tighter coupling to the hardware. KMIP is a network protocol. Clients talk to a central key manager that handles objects, policies, and lifecycle. You lose some low-level control, but gain centralized management and easier integration across multiple applications. When your application uses the HSM, this is what actually happens. The app calls a crypto API, like PKCS number 11 or KMIP, asking for an operation. The HSM client then authenticates into a specific partition, giving you isolation from other tenants. Next, the module checks policies and key attributes to see if that request is allowed. If it is, the operation runs on the protected key material. Finally, only the result, such as a signature, comes back out. The keys never leave the HSM. To wrap up, focus on 3 habits for every HSM design. First, isolation. Align partitions with real-world boundaries like tenants, applications, or environments, and don't mix them just for convenience. Second, governance. Define roles clearly, enforce least privilege, and make sure every sensitive operation is attributable to both a person and a process. Third, connectivity. Use standard APIs such as PKCS number 11 or KMIP, avoid one-off integrations, and document your assumptions so future changes stay controlled and auditable.